Consider a straightforward scenario. An electron and a photon encounter one another in empty space. At first glance, this seems like a simple interaction. A beam of light approaches an electron. The electron absorbs this incoming photon, takes its energy, and continues forward on its trajectory while simultaneously emitting a new photon in a different direction. This is the fundamental process we refer to as light scattering, something that happens constantly throughout the universe and forms the basis of how we see objects around us. However, when physicists attempt to create detailed mathematical diagrams and perform precise calculations describing this scattering process, they discover something rather unexpected lurking within the equations. The mathematics reveals peculiar possibilities that seem to defy our intuitive understanding of how particles should behave. In particular, the electron might emit a photon before it absorbs one, which already strikes us as unusual given our normal conception of cause and effect. But this is merely the beginning of the oddities. Deeper still, in the mathematical framework, sits something far more bizarre and unsettling to contemplate. According to the equations, the electron could emit a photon, and then, and this is the truly peculiar part, it could travel backwards through time itself to absorb an incoming photon before proceeding forward through time once more. We are not discussing this as some abstract mathematical convenience or as a theoretical fiction useful only for computation. Rather, the evidence suggests this happens as an authentic physical phenomenon that scientists can genuinely detect, measure, and verify through laboratory experiments. The trajectory of such an electron traveling backward through time can extend across such distances and intervals that it manifests as a real and measurable effect in actual physical experimentation. Take a moment to absorb what this means. We are not talking about mathematical tricks or convenient accounting procedures that physicists use to make calculations work. Instead, we are discussing something you could observe directly with instruments, something you could measure with precision, something you could verify and confirm in a laboratory setting. This is observable reality, not theoretical abstraction. Now imagine what occurs when you observe this electron traveling backward through time while your own temporal experience continues moving forward. Interestingly, this backward-moving electron appears virtually identical to a normal electron in most respects, with one crucial difference. It experiences attraction toward ordinary electrons rather than repulsion. In the language of physics, we describe this by saying it carries a positive electrical charge instead of negative. The reason for this apparent charge reversal becomes clear when one considers the complete effects of electromagnetic field polarization, which explains why a backward-moving electron appears to observers as having opposite charge characteristics. Because of this peculiarity, physicists named this particle the positron. The positron represents a sibling particle to the electron, and it exemplifies what we call an antiparticle, a fundamental category of particles in nature. This concept opens up something profound and beautiful about the architecture of the universe. This phenomenon is not unique to electrons. It represents a general principle applicable throughout nature. Every single particle that exists in nature possesses an amplitude, a quantum mechanical probability, to move backward through time, and consequently, every particle has a corresponding antiparticle. This prediction came long before scientists understood the underlying mechanism. Paul Dirac predicted, based purely on following where his mathematical equations led, that in addition to electrons there must exist another particle called a positron. The remarkable aspect of Dirac's contribution lies not in his physical intuition, but in his intellectual courage and rigor. He saw what his equations told him, even when those equations seemed to predict something that appeared impossible or contradicted conventional wisdom. He followed the mathematics faithfully, even as it led toward seemingly absurd conclusions. Years later, Carl Anderson confirmed Dirac's prediction experimentally at Caltech by detecting positrons in cosmic ray experiments, providing stunning confirmation that mathematical reasoning can reveal hidden aspects of reality before experimental methods catch up. The properties of these complementary particles follow strict rules of correspondence. Their energies are equivalent, their masses are equal, their electrical charges are opposite. Most importantly, when these two particles encounter one another, they can annihilate completely, converting their entire mass into pure energy in the form of gamma radiation. We typically refer to the positron as the antiparticle counterpart to the electron, and the characteristics we have described, equal mass, opposite charge, mutual annihilation capability, define what we mean by a particle-antiparticle pair. This was far more than mere theoretical speculation or mathematical curiosity. Anderson's discovery of the positron in cosmic ray studies provided experimental confirmation of Dirac's extraordinary prediction, validating his theory in the most concrete way possible. This discovery opened an entirely new avenue for understanding particles and their interactions. Most significantly, it demonstrated that mathematics could successfully predict features of reality that experiment had not yet uncovered. The equations had revealed truth about the universe before observation could confirm it. This realization transformed how physicists understood their discipline. From Dirac's theoretical argument, it became clear that other particles in the universe should also possess antiparticles. Consider the proton, which is far more massive than an electron and carries positive electrical charge. The logic of Dirac's prediction suggests that an antiproton must exist, typically symbolized as a P with a bar drawn above it. This antiproton would carry negative electrical charge and possess the same mass as an ordinary proton. The same principle extends to all other particles. Most crucially, when a proton and antiproton encounter one another, they annihilate, releasing tremendous energy. Here emerges a point of genuine confusion that frequently arises, and it merits careful examination because it reveals something significant about what we actually mean when we discuss antiparticles. Many people struggle with the concept of an antineutron because they reason as follows: a neutron possesses no electrical charge, it is electrically neutral. Therefore, how could it possibly have an opposite charge? This question exposes a widespread misunderstanding about the nature of antiparticles. The defining characteristic of an antiparticle is not simply that it possesses opposite electrical charge. Rather, an antiparticle exhibits a specific set of properties, and it is the complete collection of these properties that inverts. Electrical charge represents just one property among many that characterize a particle. When physicists speak of an antiparticle having opposite properties, they mean the totality of its characteristics are inverted in specific ways. The antineutron differs from the neutron in a very particular manner. If you bring two ordinary neutrons together, they remain as two separate neutrons. They coexist peacefully without any dramatic interaction. However, if you bring a neutron and an antineutron into contact with one another, something remarkable happens. They annihilate instantaneously, releasing a tremendous explosion of energy. The released energy manifests as various particles. Pi mesons, gamma rays, and other decay products scatter in all directions. The explosion proves particularly spectacular precisely because neutrons carry substantial mass compared to electrons. When this mass converts into energy according to Einstein's famous equation EmC2, the amount of energy released is enormous. Unlike electron-positron annihilation, which typically produces just one or two simple photons, the annihilation of neutrons and antineutrons generates a shower of many different particles. This creates a complex cascade where energy transforms into matter, and matter converts back into energy, happening almost simultaneously in violent interactions. This opens up a fascinating speculative possibility. While it certainly stretches our imagination, and while we have not yet accomplished it in practice, if antiparticles exist for neutrons, protons, and electrons, then antimatter atoms could potentially be constructed. The physics permits it. The laws of nature allow it. Only engineering challenges and practical difficulties stand between us and such a feat. Consider a hydrogen atom, the simplest atom in existence and a fundamental building block of the universe. A hydrogen atom consists of a single proton at its center, with an electron orbiting outside. It is elegant in its simplicity. Now imagine if we could somehow create an antihydrogen atom, an antiproton at the center, with a positron orbiting around it in the antimatter equivalent of electron orbitals. Would such a system function? Would it remain stable? Would it behave identically to ordinary hydrogen? From a physical standpoint, the answer appears to be yes. The antiproton carries negative electrical charge while the positron carries positive electrical charge. These opposite charges attract one another, just as the negative electron and positive proton attract in ordinary hydrogen. The masses are identical. Every physical property matches. The electromagnetic force that binds ordinary hydrogen atoms would bind antimatter hydrogen identically. The quantum mechanical principles that govern electron orbital behavior around a proton would govern positron orbital behavior around an antiproton in exactly the same manner. This reflects one of the deepest principles of physics, the fundamental symmetry of nature. The theoretical equations seem to indicate that if one could construct a mechanical clock made entirely of ordinary matter and then construct an identical clock made entirely of antimatter, the two would function identically. The ticking would be the same. The mechanisms would operate with perfect equivalence. Every physical process that occurs in matter should have an exact mirror image in antimatter. Obviously, if you brought these two clocks together, they would annihilate each other in a tremendous burst of energy, but as long as you keep them separated, the two clocks would be completely indistinguishable. But immediately upon accepting this principle of symmetry, a profound question arose that fundamentally shook physics to its core and forced scientists to reconsider their understanding of nature. It is entirely possible to construct two clocks made of ordinary matter, one that exhibits left-handed characteristics and one that exhibits right-handed characteristics. This is not a simple thought experiment. Scientists base this on actual experiments conducted with cobalt-60, a radioactive isotope. The experimental setup proves ingenious in its design. Physicists align the nuclear spins using powerful magnetic fields, then cool the cobalt to temperatures approaching absolute zero to maintain this alignment. Subsequently, they carefully observe the direction in which electrons produced by beta decay preferentially emerge from the radioactive decay process. Here is where observation made a shocking discovery. The two clocks, the left-handed version and the right-handed version, do not operate at the same rate. The left-handed clock receives fewer beta decay electrons than the right-handed clock, causing the second hand to advance more slowly. This demonstrated something unexpected. Two apparently equivalent systems based on mirror images actually behave differently. This finding contradicted decades of accepted physical theory. For generations, physicists had confidently assumed that the universe possessed perfect symmetry under mirror reflection. They believed left and right should be completely equivalent, that nature should be indifferent to handedness. But the experimental evidence showed otherwise. This was genuinely shocking to the physics community. The weak nuclear force, which governs the process of beta decay, violates this mirror reflection symmetry. The universe distinguishes between left and right. It picks a direction, showing preference for one orientation over the other. Simultaneously, physicists had also assumed that matter and antimatter were equivalent in this regard. The belief was that if you constructed an antimatter clock with right-handed geometry, it would run identically to a right-handed matter clock. Similarly, a left-handed antimatter clock would function the same as a left-handed matter clock. In other words, originally physicists supposed that all four combinations, right-handed matter, left-handed matter, right-handed antimatter, and left-handed antimatter, would all operate identically. But now that scientists had discovered matter itself violates left-right symmetry, one symmetry was lost. The universe clearly distinguishes left from right. The question then became, what about the matter-antimatter symmetry? Logically, if left and right are not equivalent for ordinary matter, they presumably should not be equivalent for antimatter either. This led to the crucial question, which configurations correspond to which? Does right-handed matter behave the same way as right-handed antimatter? Or does right-handed matter behave the same as left-handed antimatter? The answer to this question, scientists realized, would reveal something beautiful and profound about the fundamental nature of the universe. One might dismiss this as merely an academic curiosity, a puzzle interesting only to theoretical physicists. However, this question cuts to the very heart of how nature operates and how the universe is structured at its deepest levels. Scientists performed exceedingly careful experiments using positron decay instead of electron decay in beta decay processes. The results proved definitive. The hidden symmetry manifested itself through an interconnection. Matter oriented to the right functions identically to antimatter oriented to the left. The fundamental symmetry was not destroyed at all. It was merely obscured, hidden within a more elaborate and sophisticated arrangement. One must combine two transformations, first transforming matter to antimatter, and then transforming left to right, to recover the symmetry. It is analogous to a puzzle where you thought you had lost a piece, only to discover it was hiding underneath another piece all along. Therefore, it is truly accurate to say that left-right symmetry remains preserved in nature. If you created a left-handed clock but constructed it from antimatter instead of ordinary matter, it would operate identically to a right-handed matter clock. What actually occurred is that instead of having two separate and independent symmetries in the physical rulebook, these two symmetries combined to create a single, more unified rule. This combined symmetry, called CP symmetry, where CP stands for charge conjugation and parity, became the new foundation upon which our understanding rests. The universe respects this deeper, more subtle symmetry even while appearing to violate the individual symmetries separately. It is elegant, it is unexpected, and it carries profound implications for our understanding of physics. Reflect on what this means for human knowledge. Physicists thought they understood how the universe operated. They believed left and right were equivalent. Then they discovered this assumption was wrong. The universe selects a direction. But then, and this is the beautiful realization, scientists found that if you flip both the matter to antimatter and left to right simultaneously, you recover the same physics. The symmetry has not been lost. It is simply more intricate and multifaceted than anyone had previously imagined. This principle has profound ramifications, including one that seems like science fiction, but is actually a serious scientific consideration: communication with alien civilizations. This might sound fanciful, yet it represents a genuine and practical problem that physicists have contemplated. Imagine that humanity makes contact with intelligent beings on another world through radio signals sent across space. Through years of exchanges, the two civilizations teach each other their languages, their physics, their technological achievements. They share their cultures, their philosophies, their dreams and hopes. Decades of communication and mutual understanding elapse. Eventually, the two civilizations determine to meet face to face to establish direct contact. But here emerges a serious problem, a real, practical problem that actually matters. The challenge is this: how do you define right and left across the vast void of empty space? You cannot point. There is no gesture visible across interstellar distances. There is no up or down in the vacuum of space, no shared frame of reference. You cannot physically send them a sample to compare. You must describe it using the laws of physics alone. Pure physics. Nothing but nature's fundamental laws and principles. Prior to the discovery of parity violation, this would have been impossible. There was no way to distinguish right from left using only physics. The laws were perfectly symmetric, and no experiment based on pure physics could establish a universal definition of handedness. But now, armed with this knowledge about parity violation and CP symmetry, scientists can actually accomplish this. We can use beta decay experiments to define right and left universally. We can communicate with an alien civilization, build this cobalt-60 apparatus, align the nuclear spins this specific way, cool the system to near absolute zero. Now measure which direction the beta decay electrons preferentially emerge. That direction, that is what we call right. That is our definition. If the alien civilization happens to be made of antimatter, and we give them identical instructions to build a right-handed cobalt-60 apparatus like ours, their apparatus will produce results that appear opposite due to the CP symmetry we discussed. Their right will be our left, because they are made of antimatter. We tell them to perform the same cobalt-60 experiment and measure electron directions. That experiment defines right for them. We compare our results. If we obtain the same answer, both civilizations are made of ordinary matter. If we receive opposite answers, we have discovered something profound and troubling. Imagine the scenario that follows. After extensive radio communication, the two civilizations teach each other the principles of spaceship construction. They share their engineering knowledge and scientific understanding. Eventually, after months or years of preparation, the two civilizations launch spacecraft toward a meeting point in empty space, halfway between their home worlds. Both species are excited. Both are prepared for this historic moment of direct contact. They have instructed one another thoroughly regarding their traditions and customs. The two spacecraft approach one another. The crews prepare to exit their vessels and meet face to face, ready to shake hands in greeting as both species celebrate this extraordinary achievement. But here lies the danger, and it is very real. If the alien civilization extends its left hand in greeting, while you extend your right hand, you must watch carefully. That simple gesture, that one simple hand gesture, conveys tremendous information. It tells you everything you need to know about their matter composition. If they use right opposite to how you use it, your physics experiments produced opposite results, meaning their civilization is constructed from antimatter. One touch, one point of contact between matter and antimatter, and both beings would vanish. Both spacecraft would probably annihilate. Everything in the immediate vicinity would vanish in an enormous burst of gamma radiation, the most tremendous explosion imaginable. Every atom of mass would instantaneously convert to pure energy. So if you encounter an alien civilization, remember this lesson. Do not shake hands until you have verified your respective beta decay experiments. Do not make physical contact until you have confirmed that both civilizations are made of the same type of matter. This brings us back to contemplate the eternal dance of creation and destruction that lies at the heart of all physical reality. When a particle and its corresponding antiparticle collide and meet, they annihilate one another completely, and in their place, new particles emerge. For positrons and electrons annihilating each other, the products are typically one or two photons, though sometimes more photons appear depending on how much energy was locked into the system. All the energy that existed in the form of mass, the rest energy given by Einstein's equation, gets released as pure electromagnetic radiation. This radiation propagates outward in all directions at the speed of light. Consider what this means. Complete conversion. Mass transforms into energy. Nothing remains behind. No matter persists. The process is perfectly reversible in nature's accounting. Just as matter and antimatter can annihilate to produce photons, the reverse process also occurs. Photons carrying sufficient energy can spontaneously create matter-antimatter pairs. This process happens constantly throughout the universe. In particle accelerators, where scientists collide particles at tremendous speeds, in cosmic ray collisions with the upper atmosphere, near black holes where gravitational fields concentrate enormous energy, anywhere sufficient energy gets concentrated in a small enough region, particle-antiparticle pairs materialize from pure energy. This occurs right now, continuously. Cosmic rays strike Earth's atmosphere and create particle-antiparticle pairs. Most annihilate almost instantaneously, vanishing in a flash, but scientists have instruments sensitive enough to detect these transient events. Now consider photons themselves, which exhibit an interesting property. Photons appear exactly identical in all respects when traveling backward through time as when traveling forward, as we considered earlier. Therefore, photons are their own antiparticles. Physicists have cleverly incorporated this into the broader framework so that photons become an exception that illustrates the rule perfectly. A photon moving forward through time is absolutely indistinguishable from a photon moving backward through time, so each photon serves as its own antiparticle. Photons carry no electrical charge and make no distinction between particle and antiparticle forms. They exist in perfect temporal symmetry, completely symmetric in their behavior with respect to time's direction. This interpretation of particles moving backward through time explains something remarkable that Dirac's original theoretical work left unexplained. Dirac asserted that antiparticles must exist, and history proved him correct. However, his original theory never really addressed the fundamental question, why must antiparticles exist? What is the deep reason? Why is the universe constructed this way? When you contemplate particles moving backward through time, suddenly everything becomes clear and comprehensible. The existence of antiparticles becomes not an optional feature, but a necessary consequence of how particles behave in spacetime. When scientists observe pair production, an electron and positron materializing from pure energy, they are actually witnessing something more elegant, a single electron's world line making a U-turn in time. Think about that imagery. The positron is not a separate particle that was created. It is the same electron, now traveling in the opposite direction through time. It is one electron making a U-turn. When scientists subsequently observe annihilation, where an electron and positron encounter and destroy each other, they are viewing that same U-turn from a different perspective. What appears from our viewpoint as two separate particles meeting and destroying each other is actually one particle's path doubling back on itself in time. The creation and destruction are optical illusions generated by our restriction to forward-moving time. We experience the universe moving forward through time only, never backward. Therefore, when we observe something moving backward, our brains interpret it as an entirely different kind of particle. But it is not different, it is the same particle. The electron never actually appears or disappears. It merely changes direction in time, like an automobile making a U-turn. Same vehicle, just turned around and heading back where it came from. This perspective, strange as it may initially seem, actually works perfectly with experimental observations. The calculations derived from this interpretation match experimental results with extraordinary precision. Scientists achieve predictions that agree with measured reality to 1 part in a trillion. No other theory in physics achieves such accuracy. Every Feynman diagram physicists draw relies on this interpretation, permitting particles to zigzag through space-time, moving forward and backward through time, creating the rich and complex tapestry of quantum interactions that we observe experimentally. When physicists sum over all possible particle paths, including those extending backward through time, they invariably arrive at correct answers that match experiment. Nature has spoken through the evidence. The mathematics is transparent and clear. Particles can and do travel backward through time, and we designate their backward-moving versions as antimatter. It is not some exotic substance from an alternate universe. It is not fundamentally alien material. It is ordinary matter, electrons, protons, neutrons, moving through time in the direction opposite to our own experience. That is the entire story. That single insight, one profound realization, unlocks the deepest secrets of how particles interact with one another, how they are created and destroyed, why the universe is structured the way it is, and what the true nature of reality becomes when examined closely. You see, sometimes the most outlandish ideas, the ones that sound completely absurd and impossible when you first encounter them, turn out to be true. The universe contains strangeness beyond what we typically imagine, and that is ultimately what makes physics so wonderful, so beautiful, and so worthy of human curiosity and contemplation.